TSMart that enables performing differential pressure control. You know that the TSMart currently can already do flow control, power control, position control. It's a bit limited to use a TSMart with position control, which is then make it operate like a standard control valve, but we know it's available just as a backup way. And for some people that have a bit difficulties to make the step towards flow control. So it can be a way to use the more advanced features of TSMart. But one thing that we didn't do yet was to do anything with the differential pressure. And by doing TSMart DP, actually what we do is to have developed, if you want, an electronic STAP or an electronic TA pilot or an electronic DA516. It is performing essentially the same function, but you will see there are some significant differences. We are going to go through this. And we'll see the reason why we come with TSMart DP. Obviously, we are going to see the connection schemes. We are going to see the wiring. We are going to see how to configure it with the app, the kind of errors that can be raised, and anything that goes basically around this TSMart DP. So let's start and enter to the core of the topic. I like to start with a good reminder on differential pressure control, because I believe it's certainly not a luxury to do so, and I need it somehow to be able to compare the TSMart DP, electronic delta P control, to what we are used to with an STAP, to make it simple. So we start with this. We have this is the very traditional way we introduce differential pressure control, right? So we get variable flow in a network inducing variations of differential pressure in the system. So the available differential pressure on a given circuit is changing over time, increasing, decreasing, etc. This is symbolized here by the animation. We get, as we are used to, a measuring valve, a DP controller, here an STAP. This STAP, being a self-acting DP controller, has a membrane and a spring. We read through the capillary pipe and the drain connection of the valve the P1 pressure. Through a channel inside the device itself, the valve itself, we can read the P2 pressure. P2 is on the bottom of the membrane, P1 on the top of the membrane. Therefore, the difference between P1 and P2, the stabilized delta P, is applied on the membrane. This creates a force to close down the STAP while the spring is pushing up to keep it open. And the balance of these two forces gives us a stable solution. So at one moment in time, we are getting a certain available differential pressure at the inlet of the system. We get a certain stabilized value, dP, that is quite okay for the moment. And we get, of course, the DP controller open at a certain opening, therefore having a certain pressure drop. The sum of the stabilized dP and the dP of the delta P controller is equal to the available differential pressure if we neglect the delta P, the typically 3 kPa of the measuring valve, to make it simple for the explanation. So let's assume that over time, something is happening on the primary system, and we get an increase of available differential pressure. And before the system, that is a mechanical system, has the time to react, well, this variation of differential pressure will transit in the flow at the speed of sound, because pressure waves are circulating at the speed of sound, basically. And at the speed of sound, the increase of pressure is propagating and will induce an increase of basically flow, and therefore pressure drops everywhere. So every one of these previous pressure drops will increase by the same percentage as the available differential pressure before this delta P controller has the time to react. And here I am forcing a little bit the explanation. Of course, the DP controller doesn't wait. It has a certain inertia, yes. It does not react immediately, yeah. We slow it down by the capillary pipe. So it takes, we know that 1, 2, 3, 4 seconds maybe to react, but it's not like it's waiting long. Eh? But still, now the DP controller can feel an increased difference between P1 and P2, so an increased delta P stab on the membrane. This means an increased force on the membrane. The spring is still in the same position as before. So basically the mechanism will go down, compressing the spring at the same time until we get again a balance of force between the spring and the membrane at another but more closed position of the STAP, meaning that the STAP will therefore here get in a situation of having closed itself more, increasing its own delta P, and by increasing its own delta P, it decreases the delta P stabilized back to where it was, or almost back to where it was. As you know, this is not a complete correction, it's a proportional controller. Remember the webinar with Jeffrey yesterday. Here we get a proportional controller. An STAP doesn't have an integral component, doesn't have a derivative component, but it is a true P controller, a proportional controller. So that's the very usual thing. Now, linked to that, we have the usual performance curve of a delta P controller, where in vertical axis we have the stabilized delta P, in horizontal axis we have the flow. And what we know is that when the flow is increasing, the differential pressure controller is opening and opening and opening, and at a certain point, he will arrive to be fully open. And this is the place where, when the flow continues to increase, the delta P of the delta P controller starts to increase with the square of the flow, and therefore the load is decreasing with the square of the flow, and we get down. Reciprocally, if the load is closing, if the flow is decreasing in the load, the DP controller will shut, and shut more until it is fully shut there when we are at the vertical axis. Typically, we look at two extreme positions. This position where the DP controller is fully open, and this position where it is almost fully shut. And we take the values, the extreme value of the delta P in these two conditions, and we find out what is the P band of the delta P controller. This is the proportional band, the way or the place, the variation of differential pressure when the controller controls proportionally the control variable it is dealing with. If we force the full closure of the load here, what is happening, and this is peculiar of self-acting DP controller like an STAP, like a TA Pilot, like a DA516, well, the delta P is increasing on the membrane, and in some way there is a sort of acceleration mechanism where the DP controller is able to close faster than the load, and therefore it will let a little bit of the available pressure to go on the load when it is fully shut, but not so much because it's closing faster than the load, and it prevents that the increase of delta P on the load is too big. This little increase of the load, delta P, at closure of the differential pressure controller, we call it the ceiling pressure. This shows what the controller is able to really intercept as differential pressure. It doesn't let more than a few kPa going on the load when going to zero flow. And these are two essential parameters: the P band, having a P band that is not too wide, cannot be too narrow, otherwise it would not be stable, but not too wide, it's important, and we know that some differential pressure controller on the market are absolutely disasters in terms of P band. And then you get the ceiling pressure, and this is all about the ability of the delta P controller to go correctly and fast to closure when the load is closing, and to go actually faster than the load, otherwise it would let the whole available differential pressure to go on the load. So we get this essential piece of element in mind now for what is differential pressure control. Let's look now at TSMR-DP. Well, what is an electronic delta P control valve or an electronic delta P controller? So first, the question is why? Why do we have a TSMR DP? Why did we develop a TSMR DP? Well, the main reason is in terms of application, what we can do with. We are able, with a TSMR DP, to provide flow, power, energy, temperature monitoring to people at the place where the TSMR DP is connected, same as with TSMart, obviously. But this time, while we are able to separate the hydronic network into pressure-independent zones, while the valve acts as a delta P controller. And this is something that can be interesting depending on the applications. We are going to see one example, especially now. But the second reason why we went with a TSMR DP is that beside just the thinking about the possible application of it, we have been facing, of course, a competition. And this competition comes again from Belimo with the Belimo EDPV, which is a variant of the Belimo energy valve. And you can see an illustration from one of the documents of Belimo where you see the energy valve, the local temperature sensor, the remote temperature sensor, the delta P sensor element, and then one more temperature body for taking the P1 pressure and a fourth one for taking the P2 pressure. That makes a lot of plumbering clearly here, huh? But we are going to speak about that. Now, we have seen on the market, on the French market, which is quite an important market in Europe, that Belimo has been doing some work on this French market and has been promoting the use of the EDPV extensively in France, especially in Paris area, in office buildings. And it is made to control each of these Belimo energy valve, EDPV, are controlling a zone where the terminal units are then equipped with manual balancing or TBVC, TBVCM-like valves. One thing that is also good to know is that we were expecting this to be spread in different countries, but actually it's not. Right now, but maybe you have seen it yourself, but right now we don't have information about having the EDPV anywhere else than in France. We have tried to get it in different countries, and the answer was that it was not available as a valve. It's still in development. And even in France, when it is sold and it is gray. It is not colored like in some marketing document they have got. It's like a gray valve, like we don't know what is the exact stage. So it is sold indeed on some project, but it doesn't look that standard way to approach the sales as they do with other products. So there are mainly two reasons. There is an interest in terms of application. We are confronted to a competitive market, or a market where Belimo came up with a valve, where the French customers have been assigning their designs in office buildings to this kind of setup. And therefore, if we want to get a share of this market and not to be out of this project, we needed to get a valve that was able to do that. So we started to work on TSMart DP. The general principle of operation is the following. About this application, we get a number of terminal units here, right? 1, 2, 3, 4. Here I have drawn with a TBVC by the symbol. Okay. We get a TSMart DP. We get the remote temperature sensor of the TSMart DP because it's a valve like the TSMart that is able to measure the delta T, therefore can monitor the power or control the power and can monitor the energy. And then we have a delta P sensor that is connected on the supply and return pipe, and that allows simply to measure P1 and P2 to get a measurement of the delta P across the branch, in front of the branch. And according to the value returned in a 0-10 volt signal by the delta P sensor, the TSMart DP is going to control the delta P at the inlet of the branch. So the first thing that we can say is that the delta P sensor measures the delta P to be stabilized, right? This is P1 minus P2. The 0-10 volt VDC output of the delta P sensor is connected to the analog input of the TSMAR DP. And in this way, the TSMAR DP is able to read the delta P and to react accordingly. But that means as well that the analog input is no longer available for anything else. With the TSMAR DP, you cannot use the 0-10 volt input signal because it is confiscated by the delta P sensor. The delta P sensor is connected to it. You would be able, however, to control the valve with other control mode if you control it through bus communication. About the way it works, the TSMAR will open and close itself to maintain the delta P stabilized P1 minus P2 at the selected set point, what has been defined when you configure the valve. Just what you do with the Allen key on the STP. When you are adjusting the STP, you are defining that the STP should stabilize, for instance, 25 kPa. And if this is configured via iTunes that the TSMAR DP has to stabilize 25, it will open and close to keep the 25 kPa in front of the branch where the delta P sensor is connected. As I mentioned before, it is possible to set flow or power control, but then it will have to be via bus. You cannot do it anywhere else, of course, because the analog input, as I mentioned, is confiscated by the delta P sensor. And this is maybe a possibility if you want to use the delta P reading not for delta P control, but for delta P monitoring. And we know that there has been a couple of discussions on different projects with customers about the possibility to do this kind of things. So these are the very general principle of operation. A delta P sensor reading the stabilized delta P, reading the delta P to be stabilized, sending the value of it through a voltage signal to the input signal of the TSMAR DP, and the TSMAR DP is controlling to keep this value at the right value of the set point that has been configured to the valve. Let's look now at some particularities of operation of electronic DP control. The first is that we get a very narrow P band. So the TSMAR DP will maintain 25 kPa, but not with a very, I would say, slopey P band. It is a quite narrow P band. It's fixed all over the range. And the particularity of it is that this is not so much the P band that plays a role, but some amount of hysteresis that has been programmed into so that we prevent permanent actuation by the actuator that would try to compensate the very small variations of pressure. You all have used the T-scope on the valve, right? And you know how bumpy is the reading of delta P when you make this reading on the valve. And it is the same, obviously, when you get a sensor sensing the stabilized DP between supply and return, you get the reading that goes up and down by little amounts, but still, if we would not cut a little bit the reaction of the TSMAR DP at some point, the actuator would permanently move, and that would kill it away over time. So there is some amount of hysteresis, but a very narrow P band. Now, there is a main limitation to the electronic DP controllers, and this is the speed of their actuators, right? I mentioned in my very first slide that a self-acting DP controller is able to close faster than what the load is doing, because there is a sort of accelerating mechanism with the combination of the membrane and the spring. And when the delta P tends to increase, At the moment you go to 0, the self-acting DP controller will close fast, 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 and will prevent that delta P is increasing. With an electronic delta P controller, when the load is driven to 0 flow, the actuator cannot accelerate more than what the actuator itself has as an intrinsic speed, and it will not be able to catch up and close before the load is fully closed. Meaning that most of the time, unless the load is really closing relatively slow, most of the time the load will be the first to close. And if the load is the first to close, then the full available differential pressure goes on the load. So there is no way that the delta P can be kept at an acceptable level here. You get the full available differential pressure applying to the load. So that's a limitation that has to be known. This means that an electronic DP control should not be used if a load can fully close, or then you have to implement a minimum flow setup, but that can be expensive, right? Or simply you accept that the full available differential pressure may be applied to the load, correct? Now, this being said, the application where we have seen this going, as I mentioned earlier in France with the Belimo EDPV, are zones of a building, typically a floor, with quite a few terminal units, and where basically the way it works, or the assumption that is taken, is that there is never all the terminal units closed at the same time, or it is not happening in normal circumstances. It might be as well that some minimum flow has been implemented somewhere in the system by a discharge valve, maybe by a three-way valve on one of the terminal units, or by other minimum flow mechanism, like, for instance, we had seen that before, but a compact P in a bypass, or other ways, even possibly, that could be chosen. Okay, so that's quite important, and we will see some test results that will show you that in a good way. Let's look now at the connection schemes and the delta P sensor sets. How to connect delta P sensor to P1 and P2. In the case of Belimo, on the picture is relatively clear. You need to install the energy valve, and then 1, 2, 3, and 4 temperature bodies. This is huge work, right? Certainly not a good thing for the installer. And by the way, the installers, case in France, got away from that and made their own way, as I will show you in some later slides. In the case of the TS-Smart DP, what we did during the engineering of the TS-Smart, we already knew that we wanted to go to the Smart DP, and therefore we have prepared for it. And all the temperature bodies that we have released have a connection point at the bottom of it. This is here the place of the temperature pocket, and here you get a G116 connection point with the typical small G116 plug, same as the one you get on the STAP bonnet, right? So if you remove this little plug, you can come here and connect a capillary pipe, as we will use to connect to the delta P sensor. And we did something similar on the large TS-Smart. You maybe have noticed already that we get 2 little plugs there, and these 2 little plugs correspond to the upstream pressure to the valve and the downstream pressure to the valve, meaning that we can always avoid to make any difficult connection to the piping with a capillary. We can use, at least for one of the 2 pressures, either the temperature body, or if it's a small TS-Smart, or we can use the TS-Smart itself to connect one of the capillaries. In terms of connection, well, this is it. In the small version, you get one temperature body for the remote temperature sensor, that's clear, and therefore I can go with my capillary on the bottom of it. It's easy to connect. And then on the other side, I get my capillary connected to a special adapter. We will see what it looks like, but it's basically an adapter from half inch to be simply screwed onto an extension that would have been soldered on the pipe, and it's quite standard to be able to go into half inch. And then this adapter has itself female G116's space to be screwing in it the second capillary. What you see as well is that we get an electrical connection box to make the interconnection between the sensor and the smart box. This is not provided. We'll come back to this. Customers will have to make the wiring themselves. We have the wires provided, and the wiring diagram is relatively clear in this respect. We get the available differential pressure here. We get the stabilized delta P here, and we get simply this operating. Here is the first scheme. Because we are more used to see DP controllers on the return, I took the first connection scheme, on the return. But we obviously can do absolutely the same with the TSMart DP on the supply, and then we just simply have to change the way it is connected. And by the way, we get the same on the large valve, but on the large valve, one of the capillary pipe goes onto the valve and the other goes onto the pipe, similarly as we get here on the other side with the small TSMart. So these are the typical connection schemes that will enable to make the TSMart DP to operate. Now, we have three available sets that will go with the TSMart DP. The first set will be a delta P sensor set where you can specify a delta P to be stabilized between 10 and 100 kPa. It is composed of a TA-Link. It's not an existing TA-Link that we have in the datasheet. It's a new one, a new version of it. It's the TA-Link 0100 kPa that gets an output of 010 VDC, and that has get a higher burst pressure than what we get used to. This is a burst pressure of 5 bar. We get two connection pieces, 6mm copper pipe, two internal G116s. This is to fit in there to be able to screw in it the capillary pipes, typical capillary pipes, exactly the same as for the STP. And then these two connection pieces that I mentioned to you, which are external half inch to internal 1/16. Now you will wonder, why do you have two? Because actually in your connection scheme, you only need one, right? One here or one there, or even one here or one there. Every time we need only one. Well, you will see in a minute that there are cases where we might need a second one, and this is clearly not very expensive. So to have the kits or to deal, we avoid too much complexity actually in terms of variance of sensor sets, we have defined it in this way. We now get a second delta P sensor set, which will enable to stabilize anything between 40 and 400 kPa. It is made of a TA-Link 0400 kPa. Its burst pressure is 12 bar, and then you get all the same connection piece. And then finally, we get a connection set, no TA-Link, only the connection set. Why is that? Well, simply because on the market where they already use that, what has happened already to Belimo, it's the same story as for us. Belimo doesn't have any delta P sensor. As we do, they are buying it from a supplier, and they get it rebranded. Now, customers are not that stupid, and they notice that they could buy the same delta P sensor directly from the supplier at a cheaper cost than what Belimo is selling to them. So they started to work on the market by saying, yeah, we don't need your DP sensor, we'll buy it ourselves, just provide us with the connection pieces. And if we want, of course, to take market share, well, we have no other choice than to be able to provide this freedom. So we have got this possible, but of course, to make the TSMart DP to work, the people will have to use exclusively the same DP sensor as the ones that we have prepared the TSMart DP for, because the TSMart DP doesn't allow any other. And if other delta P sensor would one day be wished to be used with the Smart DP, it will need to be tested and then validated by engineering and then to be entered as new variation into the firmware and into the iTunes app. So that's not going to be an immediate thing. Let's talk now about installing and wiring TSMart DP. Well, as shown before, there is a simple connection option. The simplest is to get the TA-Link here, to get it wired to the electrical connection box and then to the input of the TSMart. You get one of the capillary pipes that gets under the temperature body. You remove the little plug, you put in the capillary pipe, and then you connect here the capillary pipe into this adapter onto a 1/16 female thread that you would have adjusted into the piping. This is by far the simplest connection. One of the issues with that is that you have to be careful because there is a burst pressure of 5 bar. Clearly, if your static pressure in the system is higher than 5 bar, you are going to get a problem because when you will connect this, you might have one side to the atmosphere and one side into the system, and therefore you would kill the delta P sensor. With 5 bar, you are quite okay for a significant number of installation. The other sensor, the 40 to 400 kPa, can accommodate 12 bar. But if you want to be safe, then you would need to implement something similar to this, which is what a number of installers have started to implement on the French market. This is a bypass with 3 ball valves. And basically what you do when you are installing the TSMart delta P sensor, you are simply opening this valve to make sure that you are bypassing between the two sides so that you get the same pressure applied on both. Before you do that, basically, you are isolating here and here from the network. You are opening here to get the same pressure, and you are doing your connection in a safer way by having bled off probably the things before. And once you are ready to go into operation, you can open one side, open the other side, and then finally you can close this valve to apply the delta P on the delta P sensor. Some of you will comment, why didn't you use the small ball valve that is available on the TA-Link, right? Yeah, good question. We went the way with the burst pressure being higher, considering that should be quite okay. We have seen what was used on the market already where it is being used. And we have also considered the cost of this little ball valve in front of the TA-Link, which is just outrageous. So if we wanted to be competitive, we simply could not get this little ball valve. This little ball valve is just unbelievable in cost because of very specifics of this small ball valve there in front. So we have decided not to include it. In case of the large DP controllers, well, it's quite similar, but you get one capillary pipe into the valve, one capillary pipe into the pipe. You have an alternative to get 2 capillary pipes into the pipe because we provide these 2 connectors. This is when you have to go and read the pressure more remotely, more away. And also to be considered, the distance here can be increased because you just need to increase a little bit this cable, not too much. It's a 0-10 volts. So you have to be careful. If it is too long, you will get induction. That's not so good. If you need even more distance between the supply and the return pipe and with respect to the place of the delta P sensor, you can, of course, extend the capillary pipe with the usual extension kit for capillary pipes as we have for the STAP. And the final connection scheme is this one, similar to what I've shown to you already. And that is being used in France by installers. Good. Now, about the wiring. The wiring is relatively simple. Good thing is that there is a full consistency in terms of cabling, in terms of use with respect to slider, right? So we get the delta P sensor with a brown cable that is the live, a white cable that is the neutral, and a green cable that is the signal, just the same as TS slider. This is not by chance. It was thought through when we worked with the TS slider initially. We looked at all the possibilities for the future, and we have tried to take the things that were making more sense so that we would not be in strange situation. As you can see, you need to power supply the sensor. So we use the connection box to be able actually to transfer live power energy, power supply, 24 volts to the delta P sensor here. So we connect to the live and the neutral, correct? And we take the signal out of the delta P sensor into a connection point here. And from this connection point, we take a wire that goes into the Y signal of the TSMR-DP. We can, of course, also read the feedback signal of the TSMR-DP, but this is independent from the delta P sensor. This is when you do a pure analog connection, but of course, you can use the TSMR-DP with IP connected to it, or RS485, or both of them if you are cloud connected and doing Modbus RTU, for instance. So everything is possible there to be combined. In terms of the analog control, you can see here clearly that your 0-10 volt input is confiscated by the delta P sensor. You cannot come with anything from the BMS into the Y input. It's already used by the delta P sensor. About the TSMR-DP selection, it has been developed into iSelect. So you go to the individual selection tab first to see the individual selection, and then you have a new section which is Smart Differential Pressure Controller, and into it you are able to first input some key parameters, the flow clearly as usual, or the power and delta T, and then you can not give it. But usually for delta P controller, it would make sense that you indicate what is the delta P to be stabilized, or at least roughly the value. So you can input it, you can make then a suggestion, and you will end up with a first table showing you the available TSMR-DP for this, the best being in green here and being the TSMR-DP 40 with a minimum DP of 16.1 kPa. If I select this one, then I can see some accessories for the valve in terms of connection because it's a small one below DN50. Then you see as well the available delta P sensor sets. You get the delta P sensor set 10 to 100 kPa here, and you get a delta P sensor set 40 to 400 kPa, and a connection set that is available there. If I am clicking on the delta P sensor set 10 to 100 kPa, I am then seeing what is inside the set, which is integrated into. It is a TA-Link 10 to 100 kPa, bus pressure 500 kPa, capillary pipe 1 meter, it's 2 pieces of it, transition nipple, and transition nipple here. If you do a confirmation, you will see the details of these. Good. Next is about the selection of the TSMR and TSMR-DP. I need to let you know that there is a new parameter that will come in. So far, the best TSMR or best TSMR-DP, we have defined that this is the smallest DN of the valve that enables reaching the required max flow, correct? That can lead us to delta P that are up to 35 to 40 kPa. So coming from some demands, we have implemented a new feature in iSelect, giving the best TSMR-DP as being still the smallest DN that enables reaching the required max flow, but also for which the delta P remains below a target value. For instance, 25 kPa, we have given that as a default value, and this is a technical parameter that is now defined in the software. Meaning that if you select the TSMR for a certain flow, and there is one of the valve size that required 38 kPa fully open, it will not tag it as being the best. It will take the one diameter larger to avoid that the minimum DP of the valve, or the DP of the valve when the valve is fully open, gets too big. Of course, if you want to release that, you can simply get a value that is relatively high, like 40 kPa, and this will not play any significant role any longer. So now, hydraulic circuit calculation with TSMR DP, you can see that we have completed a little bit the balancing type. You get a new option, which is electronic DP control. So you get this kind of scheme visible there. Side is chosen in the step 2 of the wizard. And you get then, once there is a selection that has happened, you are getting this kind of visualization where you see that I have a DP of 35.9 kPa, the DP min is 16.1, the delta P sensor set is 10 to 100 kPa, I need to stabilize 46.8. All of these values are indicated, and you see how the valve and the DP sensor are represented to look correct with respect to the hydraulic circuit calculation. Little comment to add, we also are getting, and I forgot to mention that in the previous slide, but batch selection is available as well, and direct selection, of course. Let's now look at some delta P control tests and performance. I have first here some test result that we have obtained in the lab. It's the delta P that is stabilized in function of the time. So the value in gray is the delta P stabilized. The curve in yellow is the delta P of the valve itself, meaning this is the delta P of the TSMR DP. And the delta H is the available differential pressure on the system. We have been trying to stabilize here 0.1 bar or 10 kPa, okay, right on this value there. Left axis is on the stabilized DP, right axis is for the DP of the valve and the available differential pressure in bar. So you can see here a situation where we had an available differential pressure that was not very high, and basically the pump was running at 5 Hertz, is what is indicated here. And then by steps, we have increased the speed of the pump by 5 Hertz. From 5 Hertz, we jumped to 10 Hertz. And jumping to 10 Hertz, turning twice as fast, the pump has developed suddenly a higher available differential pressure. And as you can see, immediately the stabilized DP went up way beyond the 10 kPa we needed, and the smart DP controlled it back to bring it back at 10 kPa. And then we increase again from 10 Hertz to 15 Hertz, and the smart DP brings it back. From 10 to 15 and back, from 15 to 20 and back, 20 to 25, 25 to 30, 30 to 35, 35 to 40, 40 to 45, etc. I might have missed a step, but we went up to 50 Hertz and then down again. Notice here that when we were at this speed, we were reaching an available differential pressure of about 6.4 bar, 640 kPa. And you can see the smart DP was maintaining the delta P relatively close. There is a little bit of a stop there. It doesn't control forever, as I told you, otherwise it would always having the actuation moving. But as soon as it gets within about half a kPa of the target, it stops moving. We are here seeing then the decrease of differential pressure when we decrease the speed of the pump from 50 to 45, 45 to 40, etc. by step of 5 Hertz. we get down, and you can see the opposite way, where the TSMart is constantly bringing back again the stabilized dp to the value that we wanted, or close to the value that we wanted. So this is already quite an interesting performance here. We have, of course, tested the EDPV. I don't have so good curves right now. We need to extract a little bit more of data. But I can tell you there is nothing comparable there. The EDPV of Belimo is extremely slow. So while you can see that we are controlling within something like 5 seconds-ish, the DP back to its set point, 5, 6, sometimes seconds. In the case of Belimo, it can take 2 to 3 minutes to bring back the stabilized delta P to the value. And this is simply, well, what we believe, because the algorithmics of control they are using is not stable enough. They cannot go faster. If they would go faster, they would be unstable. And we know that because every time we were blocked in the lab about trying a way to make the valve work in a stable way, the easiest and most straightforward way to get it working is to work very slow. But that's a little bit easy way. The TSMart DP here is able to control in a relatively fast way. Fast, but not faster than self-acting delta P controllers. And this is about this next one here. It's another test where we are stabilizing the delta P across an STF. The STF is considered as being the load. The STF was set at 3.3 turns over 8. It was an STF 65. Then the operation here was to decrease the setting by 0.1 turns of the STF every 5 seconds, from 3.3, so 33 positions down. We have simply here, as you can see, this is the KV of the STF starting there, and we have started to decrease the setting of the STF. And as we decrease the setting and therefore the KV of the STF, what you can see is that gradually over time, the valve is repositioning itself and taking an increasing delta P, and it is bringing you back constantly to the same value of delta P. In this case, we were stabilizing 100 kPa and trying to keep 100 kPa constant over the load. At some point when we close the load here, there is a point where the next setting of the STF, you get fully closed. So it goes fast. You are almost closed and then closed. And you see that, unfortunately, the electronic delta P controller is not able to close fast enough. It follows at the speed of the actuator. It is closing, but unfortunately, because it is closing slower than the load, the delta P on the load is increasing to the total available differential pressure, which was 4 bar. So this is what I explained exactly at the beginning here. An electronic delta P controller is not a delta P controller that can prevent the available differential pressure to go in all circumstances on the valve. It will not be able to prevent that. It will let it go when the load goes to 0. We have the red dashed line are just indication for you to see plus minus 10% on the set value, so that you get an indication on how the Smart DP is able to stabilize. Good. So as a final part here, let's now look at the configuration of TSMart DP with iTune. First, TSMart DP will only be available from firmware 3.0.0. Well, it will be available by being ordered, okay, as an article number, and all TSMart DP will come with a firmware which will get an increment. Currently, we are in firmware 2. something, and we are going to 3. something with the TSMart DP. This is a way also to manage the general compatibility between the different versions of the firmwares. You can see here in the advertising screen that we get the TSMR DP identified, and you can see the little illustration showing you the TA-Link beside the smart. So already there you can see visually and by reading that this is a TSMR DP. If I touch, of course, this, I am connecting to the TSMR DP, and there I can see a number of things. I can see first the live delta P value, where we see the main variable, the delta P. I can see the gauge for delta P. It indicates graphically the percentage of the delta P with respect to its assigned set point. In this case, except the transit time, normally you should get the gauge always almost full or a little bit beyond full, because you should get to your right value of the set point. I have set 25. I am obtaining 25.2. You can see that I'm just a little bit beyond 100% of my set point, so the gauge indicates me that. You then get the configuration frame where you can see that the valve is in DP control mode. You can see it from the color of the gauge, gray for DP, and then you can read as well the delta P set point. If you touch now the config frame, you enter the configuration menu. If you go to the application, you can recognize you get updated application schemes and text. You can still choose between supply and return according to how it has been installed. You get the control settings screen where you get all the settings from the control. First, of course, well, it's already set, but the fact that it's in DP control. Then the DP sensor that can be chosen in a list of two, the TA-Link 0100 or the TA-Link 0400, 5 bar, 12 bar, bus pressure respectively. And once you have chosen a TA-Link, it is defining also the signal, meaning that this signal is locked and you cannot change it. The characteristic of control cannot be changed. It's fixed to linear for delta P control. Doesn't make any sense to put an equal percentage characteristic on the answer from the delta P sensor. That would actually make the control more difficult. Changeover, it's already an entry that is visible, but that will become only available from firmware 4.0. This is to come. If you try, at the conference you will do it, but if you try with a firmware 3 to go to changeover, it will tell you you need first to update your TSMart to a firmware 4 to be able to use this function. In terms of control limits, we'll see that on the next slide. Temperature limitation cannot be used with delta P control. That's not making any sense. If you are doing differential pressure control, you need to stabilize the delta P across a certain area of your hydraulic network, and you cannot leave this all of a sudden because your return temperature is quite not right. Where it works a little bit when you control the power or the flow of the unit, because flow, temperature, and power are interconnected together. With the delta P, doesn't make any sense. So no temperature limitation whatsoever when you are in delta P control mode. And then finally, the input signal cannot be edited, the control source neither. When you are in DP control mode, you have to be analog on the compatible signal with the delta P controller, and iTune takes care of that. You get as well then a possibility for analog output. As I am in delta P control mode, the automatic mode has set me to DP. So the analog output will show me a value corresponding to DP, and it will be with respect to the current limit, so the range of the delta P sensor. And you can also set an override type on the DP. You can put an exception, basically, as you do with override. Finally, we have some errors and warnings for TSMR DP, and I will go to 3 out of 4 of them. The first one, as you can see here, is delta P sensor disconnected. And as usual, iTune will give you some indication about what it means. The signal returned by the delta P sensor is null, while the flow runs through the subsystem it is measuring. So clearly, there is a delta P sensor. It is measuring the DP across a subsystem. The TSMART can see that there is a flow, but receive the information that there is 0 DP. This is not possible. That means that either the delta P sensor is disconnected, is damaged, or that its cable has been cut. Correct? So these are indications about what should be checked, but when there is a flow, there must be a delta P. It cannot be null. The second one is a warning. Available delta P too low for reaching the delta P stab. It is indicating that the stabilized delta P set point is not reached. So you have asked to get 25 kPa, and you do not get the 25 kPa despite the fact that the valve has opened itself fully. So the conclusion it is giving to you is that it is very likely means that the available differential pressure for this system is too low. You are not giving enough pressure to be able to reach 25 kPa because by being fully open, the TSMART cannot let this 25 kPa go on the load. There is not enough available differential pressure. And the last one, well, the third out of 4, I will come to that, is the fact that the load KV, the KV of the load, is too high for reaching delta P stab. That's another one. It's a little bit different. The stabilized delta P set point is not reached, while TSMART DP has reached the defined max flow. I realize that I've forgotten to show you a picture of the control limits, but when you are in DP control mode, you can set two things. You can set the delta P set point, and you have to set a maximum flow. By default, it is the nominal value. So this is the way you are actually defining a maximum flow in terms of balancing. You are providing the stabilized delta P until the system is asking too much flow, which is, for instance, it could happen if the system would be more resistive, or sorry, less resistive than what it was planned to be. And in this case here, we have this warning. The stabilized delta P is not reached, while the TSMART DP has reached its max flow. So it is saying, no, I'm not opening more to give you more delta P. I cannot, I am already at the maximum flow. And that very likely means that the load on which the delta P is stabilized has a significantly lower hydronic resistance or higher KV value than expected, or that the defined max flow has been set too low. That's also a possibility. That the people would have simply adjusted the max flow that was too low compared to what's needed for the load. So these are the kind of information that are provided in terms of errors and warnings. There is a fourth one that I could not generate with the setup I have here. This is warning 22. The delta P stabilized is above the maximum sensor delta P. And this is happening when the sensor, the delta P sensor, is measuring a value and returning a value above 10 volts. And this is possible because the delta P sensor has a little saturation value just above 10 volts, which is good because then that allows us to know we are above the maximum. So at 10 volts on the 0-100 kPa sensor, we know that we are at 100 kPa. And when we get more than 10 volts, we know it's more than 100. And in that case, we say, warning 22, we are above what the sensor can measure. We cannot tell you what it is. It is above. You get a warning. Okay? So that is it. This is it about the TSMART DP, what it can do, how it can be configured, and how it can be installed and wired. At this stage, there is not so much more to give you. You will be able to experience the TSMART DP in practice at the Hydronic College Associate Conference. So this is clearly good preparation for that. We will circulate to you, of course, this presentation.